Hey everybody, welcome back, college algebra people. We've got a brand new section. We're thinking about section 2, all about linear functions. So the previous section we talked about functions in general, and now we're beginning what turns out to be a fairly decent chunk of our trimester together, talking about different types of functions, very specific characteristics of some useful families of functions, as it were. So here what we're tackling first off is average rate of change, which doesn't really directly get at this linear function thing, but of course, ideally it builds toward that. That's kind of the idea. This is one of our essential objectives, and it is to compute the average rate of change in functions on an interval, and ones in which it's possible to put in arbitrary constants. So you might have things other than just numbers. You might have like A, B, C, K, H kinds of constants running around there. Mathematicians sometimes call this the difference quotient. So, that's what we're up against. So here's our definition. So average rate of change, this algebraically looks like take some function. If we have an interval that we're operating on and A is the starting point and B is the ending point, this average rate of change looks like the function evaluated at the end minus the function evaluated at the beginning, and then divided by that difference in the inputs. So basically the length of the interval, B minus A, and then the difference in these outputs on top. Another way you might have seen this is with this Greek letter delta. So this right here, if you're into Greek life, you don't need me to tell you that, but capital letter delta. This gets used as the change in something frequently in math. So this delta meaning change in Q and then change in T as well here. And so just to sort of call out the elements here, I'm claiming that delta Q is we're calling this the total change in Q. And so basically we're just saying these, and then I guess also this numerator, these are all the same thing. So we're calling the total change in Q either delta Q or just straight up that calculation on top. And then clearly we could do the same thing for the thing on bottom. Delta T is the change in input over some interval. So we're talking about delta T or just that computation. So these folks mean the same thing. Oh good, I didn't draw something obscene by accident. Sometimes when I just draw random squiggles on a page, it can be bad. Whew, dodged a bullet. So we'll get to an example in just a second, but it's always nice to have the visual perspective. And it turns out average rate of change has a really nice visual interpretation going for it. So we usually take advantage of that when we can. So I've drawn not a random picture, but I picked something that just isn't, has a little curve to it, isn't a nice straight line. And basically what we're working with is that the average rate of change essentially says how far over and how far up and down. I'm cheating. This is allowing me to draw perfectly straight lines, perfectly vertical and horizontal ones. And so this is saying, look, and I still found a way to mess it up. Nice job, Mike. B minus A is pretty readily visible on this piece here because basically what we're saying is the distance between these two things, B minus A, is literally just, I'm going to try to use that same color here. B minus A is how far apart B and A are. That's numerically what that difference B minus A means, or geometrically what it means is that distance there, the length of that line segment. And then not maybe as clear, because whenever function notations involved, things get a little odd, but f of b is the height of the function at b, so it's the vertical height of that blue dot. And then f of a is the vertical height of that blue dot, where below the horizontal axis, the t-axis, counts as negative. So the distance between these two things actually works the same way. You start at a height of f of b, you take away a height of f of a, and that's geometrically the length of this line segment. And so the average rate of change is taking the ratio of these things, dividing this function output divided by this function input. And one cool thing that does for us is basically gives us a interpretation for this little line segment that connects the two dots directly. So we're going to get a fancy term for that. You may have heard it in a previous math class, but our average rate of change is basically how steep is this little ramp that connects two points on a function. Okay, long past time that we get an actual computation going here. So it turns out, pull back the curtain, this function has this formula. Again, if you're like me or a typical student, probably you feel a little bit of relief once we actually start looking at things with numbers in it. So we've got this formula. So this equation, the one that generates this graph for all those t comma q points, looks like 3/8 t squared minus 5/8. Sorry about the fractions. Well, really, sorry, not sorry. Our job is average rate of change in f on this interval. So we just go back to our definition, average rate of change. I like to abbreviate ARC. And sometimes we'll put a little interval. So -1 to 3. Sometimes we'll get really fancy and we'll like remind ourselves what function it is. I'm going to leave that notation off because I want to be as consistent as possible. And it's just a lot to write. So I didn't actually put any formal notation on this up here, but if I'm going to do more than one calculation, I might remind myself which of these intervals we're really looking at. There's only one function, one interval, so we don't need to get super complicated. Probably no risk of forgetting which thing we're talking about. So our basic formula is just going back to that definition. This is the great thing about having, say a note card for tests and stuff. This would be great material for that. So, sorry, this dot is going to bother me if I leave it there. All right, whew. It's that Virgo in me. Okay, here is our expression. Now it's time to actually work with our formula. So sure, that's what it looks like in general, but in order to get numbers for f of b, well, maybe let's do a and b first. So, baby steps. So our interval goes from -1 to 3. A is our first endpoint and b is our second endpoint. So this is asking us to compute f of 3 minus f of -1. And then on bottom, we're taking b, which is 3. And then this is an easy spot to miss something. I want to subtract whatever a is. A happens to be a negative number, so I want to subtract a -1. So that's actually going to end up being positive. So here's where we got to go back to our function, because and if we want to make any more progress, we're going to have to do some kind of computation with this. So for instance, f of 3 says go back to our expression here, replace all of the t values with 3 instead, and see what you get. So this is 3/8 and then 3 squared minus 5/8. And I'm going to do some brackets here just to try to track things. So this is all f of 3. And then we're supposed to take away the same thing but with f of -1. So that looks something like 3/8 and 1 squared minus 5/8 there. We have a very dramatic fraction bar for what is otherwise a pretty underwhelming 4 on bottom. 3 minus -1 here. All right. Comfortingly, I guess I need an equal sign, huh? Comfortingly, this is all some number. If you've got a scientific calculator, you could figure this out right now. We could simplify a little bit. We could, if you're excited about fractions, we could practice those a little bit and just see if we're on the same page. So this is 3/8 times 9 minus 5/8. And then the main thing I can imagine that could go wrong over here is just accidentally not distributing that negative. So we have just 3/8, and then it's actually plus 5/8 once we do minus. Okay. I think, surprisingly, given all the fractions and stuff, this comes out to be pretty nice. I think when we're all done simplifying, we're down to 3/4, which, considering what's going on the numerator there, it could have been a lot worse. And our interpretation of that is basically that if we looked at this picture, this graph over here, and we drew that straight line again, perfectly straight line. Nice job, Mike. Actually, that's not too bad. Don't be too hard on myself, I suppose. So this average rate of change says that for every 3 units up, you have to go in order to get between these 2 points. So that's 3 units up. you have to go 4 over. So that ratio between those is 3 to 4. So in any event, that's what we're looking at. Okay. One more where we do what I sort of threatened in the beginning, where instead of just having just real numbers as part of our average rate of change calculation, instead we've got some crazy constant thing happening here. We have a and a plus 1. All right, but let's not freak out. We can still do this. So average rate of change, our little interval thing looks odd, but you know what? We're resilient. We can tackle this. And so our calculation is going to look like f of whatever the second thing is, gosh, a plus 1, and then minus f of a. And then this difference is supposed to be the difference of those inputs, which, again, kind of annoying, but we can cope. So here's where we don't get rescued in the same way that we did up above. Before, we basically got an actual value we could plug back into our function. I need to make one small correction. I keep getting tempted into this whole f situation, but in fact, our function's name is not f, it is g. So let me make sure I'm consistent with the labeling there. So here is g of a plus 1 and g of a. So we're supposed to go back to our function, this new one, at minus 9. So at least it's not as complicated as the last one. But we're in charge of going back to this and saying, you know, if we want to actually compute this, we're supposed to go to our formula. We're supposed to basically carve out a spot where t, the input, used to be, and then replace it with this, you know, for the moment, just this kind of empty space. But what we're actually supposed to replace it with is whatever is inside of this function input. We're supposed to hand it a plus 1. So by golly, a plus 1 is the thing that replaces our input there. All right. So I guess, sure, we could be polite. We need some brackets. We need some parentheses. But then we're right back to figuring out g of a. And this is slightly odd, but you know what? If we're tackling g of a, that just means replace t with whatever that input is. So if I'm carving out space just like we did before, it's not a very exciting replacement. It's literally just a that we're putting in there. I feel like every one of these, there's something I could, my handwriting just is going to lead us astray. I'm going to try to make 9s and a's look very different. Last time it was 5s and s's and t's and pluses. I'm just hopeless. Sorry. All right. Our denominator actually gets pretty exciting because if we have a and then we're taking away another a, last time I checked, that's going to leave us with not a whole lot there. So in the denominator, we're left with just 1, it looks like. That's a whole lot of fraction for not a lot of denominator. And then actually in the numerator, we get kind of exciting too. So what happens here, we could do a little distribution. We could start combining some like terms. So we have 8a plus 8 minus 9. And then minus 8a from here. And then a plus 9 because we're distributing. I suppose we could write this denominator, but dividing by 1 is the same as not. So this is what we're up to. And then this is what I refer to as a Goodwill Hunting moment. So I know that movie's a little bit out of date now, but there's this moment where I guess it's Matt Damon and Robin Williams, and there's this kind of like montage excitement between the two of them where they've solved some super complicated problem on the chalkboard, and they go through and they like cross off all this stuff, all these things cancel out, and it's just, you know, very dramatic, like high five with inspirational music or whatever. So that's what we're up to here. We get to go through and cross out a bunch of stuff here because we have 8a minus 8a. We have a 9. Give me my red back. We have 9 and a minus 9. And all that's left is 8. It turns out, so I mean, fine. 8 is a perfectly good number. Nothing wrong with 8. Deserves our victory box like everything else here. But the thing is, this actually is a familiar number. What you might notice if you look back is that 8 is also, not coincidentally, this coefficient on t. It's the number being multiplied by t there. It turns out that's not an accident, actually. So what happened was, no matter what starting point we picked, if we went up 1 from that, that's an interpretation of this a endpoint and then a plus 1. So now we're digging into the symbology here a little bit. Not symbolism, but just symbols. No deeper meaning. Starting with a and then going up to a plus 1 is a jump of 1 unit, no matter what a is. And so we're saying that if you start at a, you go up 1 unit, it will always have an average rate of change of of 8. No matter what endpoint we began at, if you go up 1 unit, this thing will definitely go up 8. And so what comes next is, it turns out, it's a fairly special category of functions that has this characteristic where if no matter what point you start at, if you go up a certain amount, the output will go up a certain amount as well. And that's what we'll come back to next time.